In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most unlikely heroes make the biggest impact. Keep your mind open, your heart brave, and who knows, you might just find the ether within yourself. So here's to Dayton Miller.
All right, hello and welcome, lads and ladettes, to Ether Roundtable 109. Kat's going to do our intro, and then Shane's going to be giving us a presentation on how we know the distance to the sun. Whenever you're ready, Kat.
Welcome, lads and ladettes, to Ether Roundtable number 109, as you just heard. It is, how do we know the distance to the sun? Take it away, Shane G.
Nice. Thank you, guys. All right. So we're going to go through one of the age-old questions, or one of the thrust upon us heliocentric proofs of globularity is that everyone knows that you can confirm the distance to the sun. So let's go through what that means and how they got there. Right, so it's not transitioning this one. Cool. So starting at Wikipedia, everyone can see, right? We're on the second slide. Yeah, we're good.
Yep.
So you look up astronomical unit, it'll tell you we definitely know for sure it's 149,597,870,700 meters, right? And how they got this exact number, we'll go over. But essentially, it's using ratios and Kepler's observations of the world and plugging in the radius of Earth, essentially. That would be the factor which they measured from the sun. So we know exactly how far it is to the sun by measuring shadows on the Earth. Most of what we're going to go over is going to be based heavily on Kepler, meaning that it's only about the relative distances of the body. So the relative distance of the planets from the sun, not the actual. So whether it's how many units in millions of meters is much less important. So what the ratio is in terms of how far it is in units from this way to that way, as defined in Kepler's terms of 70 major axes of ellipses, orbits, etc. That's what's going to be important. So how they got that number obviously was to plug in some other quote known values, and that's how they got the absolute value for Earth, which then instantly told them all of the other distances to 100% accuracy, right? As soon as they got one of these, because of all the relative distances established by Kepler, they knew all of them, meaning it's just a invariantly scaled system in the first place. But we'll definitely go over that. One of the other supporting sort of correlative measurements and pieces of this measurement really is we're going to do some radar ranging to Venus, and then so we can include observing the transit of Venus, so they can observe it in two locations, and they calculate the parallax of Venus. That'll be one of the mathematical proofs that we'll actually go through. So we'll see it from their side, how they calculate that and how they think that that has validity. Moving on to the other page of Wikipedia, you'll see all these people who handily knew how to calculate the astronomical unit or took stabs at it theoretically until the guy Huygens over here, Christian, in 1659. This is widely considered the first guy who got it, quote, close. But I didn't notice this until after Alan's presentation, but right on Wikipedia, it does say that actually there was a Chinese mathematical treatise who, using shadow length tables, observed at 3 different places, and the assumption that Earth was flat did all the same things and came to the same estimation. And I've never seen that part on Wikipedia before. I thought that was funny. That is
Oh,
exactly what Alan told about in his presentation, though, how they use shadow length tables to do precisely that.
yep. And their unit of measurement, the li, was redefined to be half of a meter. So now contextually, when you look back at it, the Chinese were always half wrong about the distances to everything. Exactly half. So if the Jesuits got it 100% right, the Chinese got it half right. So if we know that the distance is 159 million mile or meters, the Chinese would have got half of that exactly, according to the recontextualization of their unit of measurement, which is just taking an arc in the sky and relating it to the ground.
And a competing hypothesis might be actually it's all just inherently ratios of things, and there's no actual value. You can assign values to that, but that becomes arbitrary when in the context of the actual ratios, which has the meaning and from Kepler and all that good stuff. Two competing hypotheses, I would say, about that. All right, so real quick, so they define an astronomical unit. They use an astronomical unit to define something called a parsec, as Alan has presented before, which is defined by this motion around the sun, but in the amount of distance that it would take for 1 arc second. So they know that the AU is involved in saying that actually we know how long this is because of an arc second, which is a minute of a unit of a circle around this side, just by knowing that actually we know this base because we know the 1 AU. So what we're going to define in terms of ratios actually has many other secondary uses where they go and define other things relative to the first ratio to then also define things like light minutes. Light minutes is like a third derivative of astronomical unit, which is a derivative of the radius, which is measuring the sun. So again, we're going to go over these units. Now, these seems to be impressive. They're expressed in units, 0.72 units. Units what? Well, this is astronomical units. So what it really is the average distance to the sun expressed as a ratio derived from Kepler. Everything we're seeing here in this column right here is Kepler. Only Kepler. No Newton, no nothing, no force, no gravity, just observations empirically of the celestial bodies and their movements in relative to each other. Now, they make it look impressive because they're saying, oh, look, now we know the distance. We know this is going to have an inherent conversion to meters. If you can convert astronomical units directly to meters, as they know we can, because as we started out, they know exactly what the precise definition is, 149 million meters. So going forward, just know that all of our assumptions that we're making, including what we're going to derive for the AU, is based heavily on our other assumptions. And in this case, it'll be a guess about one of our numbers, right? This guy, Huygens, who we talked about before in 1659, did the first actual guess. And he was able to do so by making a guess about one of his numbers. And by pure blind coincidence, he guessed correctly and actually got it exactly correct by total happenstance. I love how that happens more than once in the history of this. So how did he do it? Well, measured the apparent size, you find the distance. What he needed to actually know was the size of Venus, which he happened to have handy on him through such scientific techniques as numerology and mysticism. He knew what the size of Venus was. So plug in the dark arts, he actually used that to plug into the other side of the formula to know exactly how big Earth was so that he was able to astronomically guess correctly at the Earth's distance to the sun. Now, this is the exact story of the first dude to do it that we pointed out over here.
Have you changed slides yet?
Oh, shit, man.
Yeah.
Yeah, you guys didn't tell me?
Yeah, when you were like, this column over here, we
Dude, I noticed it first, and then I thought that
now we can see said column. Okay.
Yeah, I gotta have Canva open on top of everything. Hold on. All right.
Yeah.
That sucks. AU, right? 49 million meters. I just talked about Kepler. Everyone knows that. I just referenced the Wikipedia entry where they said exactly the same thing. There's a table, which is just the history of the people guessing the astronomical unit. And we just really poked fun at this and only talked about this guy right here, who was the only one who was close.
Dude, it's kind of like that game where you guess how many marbles are in the jar or whatever, but if you get enough people in the crowd to guess it, you average it out and it's correct. I think that's what happened here. They just had a bunch of people guessing at the distance and that guy, averaged it out correctly.
If you're the best guesser, you win the best prize. So everyone got really good at guessing.
They got so good at it.
I gotta fix OBS. There we go. All right, now we're good. So now, all right, everyone can see. So what else did we go through? Oh, when we're going through the arc angle, when we're trying to talk about parsec and how the AU, which we haven't defined yet, is going to be instrumental in defining what I call the third derivative, which is light minutes, which is how you get an actual from a parsec to light hours to light minutes, which is just one arc minute of stars, which is then defined by an AU. So one parsec is defined as the distance. So one AU subtends one arc second angle, right? So
yeah, so an easy way to think about the relationship of the parsec to the AU is if you flip this diagram sideways and you did rise over run to the Earth and Sun. So if you were far enough away, that the distance to the Sun appeared as if it was 1 arc second from the Sun, even though they know it's 93 million miles. That's how they ratio out that angle of an arc second to relate it to a parsec, which is 3.25 light years, which is, and then how they related it to the astronomical unit, which is the length of the arc second based on the distance of that. And then the ratio of that is now a light minute to traverse the distance from the sun to the Earth. That's actually beautiful how they did that. Well played.
Right. Yeah. It's a self-contained, internally consistent system. Where else have we seen that, dude? It's just beautiful. So again, the guy who first guessed it because of black magic and numerology and mysticism, and he happened to know exactly what the size of Venus was through these techniques. And it turned out he's correct, but it doesn't matter that he used dark magic and numerology. It only matters that he was correct. Like, we'll take happenstance by correctness. Anyway, if you've seen this meme, right, you say that, it's exactly, no, everyone has always been guessing the distance to the sun. This is a very popular flat Earth one. They say Copernicus guessed at 3 million, Tycho Brahe 13, Kepler 13, Newton 28, and then 54. And then Martin did 82 million, Encke did 95 million, Meyer, et cetera, et cetera. Now, that's true, and we're going to go through the formula that makes that true. But first, we're going to watch a contextual explanation from the flat earther formerly known as Jaren. This is actually like one of the first things I ever saw on the subject, and it was the background for my understanding on everything that we're talking about now. And I think that this video does a pretty good job explaining it. So we're going to go through it. We're going to go through it by clicking on it, though.
Yeah. Clicking around it, maybe?
I think I got to share sound. Forgot to do that. Now share sound. Now, do you guys hear this?
It's light. Anything else that we know?
You guys hear that?
Yep. Got it.
All right, cool. Put it a little bit up, a little bit fast, and we should be good.
About the
Go back. There we go.
All right. So it was going the first time, but this time it's not.
Oh, it skipped 30 slides. I had to find it all the way back. Okay, it went all the way to the end. I got it.
angular size. So, back to our facts. The sun emits light. Anything else that we know about the sun? Sure, we know its angular size or its apparent diameter. This is the apparent size or angular diameter of a sky item. How large something appears in our eye or telescope. The sun and moon both appear to be about 31 or 32 arc minutes, or that's equal to 1/2 degree. So I want to point out something that I certainly wasn't taught in school, and it's no wonder why. Scaling invariance. Feel free to look it up on Wikipedia, and you'll see that in physics, mathematics, statistics, and economics, scale invariance is a feature of objects or laws that do not change if scales of length, energy, or other variables are multiplied by a common factor. As long as all of your inputs are scaled correctly, the entire body is indifferent. It doesn't vary. One of those things, the entire solar system model. But wait, the mathematics of the solar system is facts. Indisputable fact, right? Well, not when the entire models are based off of angular size, because angular size tells us what size something is in our eye, not its true distance or its true size. We need more info. So hold up here. I thought...
Math is reality.
It has to be. 2 + 2 = 4. That's reality. 30 plus 15 equals 45, period. Well, is that true? A man has 30 cars and he added 15 cars. He now has 45 cars. Is this true? Well, if there was such a man, and he did add said cars to his 30-car collection, then the statement is true. Is it reality? Well, I'd have to first prove said man exists, as do his 30 cars, as do the 15 he added. That makes it reality. So is math reality? Well, only when all elements of the equation are proven true is math reality. Is 30 plus 15 45? Yes, true. Or is it? What if it was 30 plus 15 half cars? Oh, that's different. We need to prove and know what each number refers to. If I have $3 million and I add $1 million, does that mean I have $4 million? Well, if I had $3 million in reality and added $1 million in reality, then I'd have $4 million. But to claim it is reality, I must first prove that I have what I claim. So if the entire model of the solar system is based off of angular size, who has proven the actual distance and sizes of said items? Is the solar system reality, or is it a cartoon? I mean, is the solar system a fact, or is it fiction? This clearly has to be solved already, correct? What if I told you it wasn't? What if it was all just numbers? What if it was all just math, and they wanted you to believe that math was reality, but they forgot about the other part? They have to prove all the elements of the math. Let me explain. So the angular size of the sun and moon is approximately 31 or 32 arc minutes, which equals 0.53 degrees. Now, that does work for a sun 93 million miles away and 864,337 miles wide. But it also works for a sun 229 million miles away and 2 million miles wide. Wait, what are you saying? The sun would look way bigger in the sky. No, it wouldn't. It would look the same as if it was 93 million, or if it was 46,701,000 miles away and 432,000 miles wide. The distances and sizes can be scaled indifferently. Our observations from Earth would be identical. If the sun was 23,351,000 miles away and 216,000 miles wide, it would be the same as if it were 11,675,000 miles away and 108,000 miles wide. Identical to the sun that's 6,053,900 miles distant and 56,000 miles in diameter, which is no different than a sun 3,026,900 miles away and 28,000 miles wide, which is just the same as a sun 1.5 million miles away and 14,000 miles wide.
Now we're getting it.
What about our orbit around the sun? Well, sure. You know the distance, which is the radius of our orbit. 2 pi r gives us 9,504,780 miles as our yearly orbit. Divide that by 365 and that by 24, and you get 1,085 miles per hour as our new speed instead of 66,000 miles per hour. And our observations change none. And since you feel no spin or travel at all, well, then nothing changes at all. Man, math is so reality. Whether the sun is 756,730 miles away and 7,000 miles wide, or even, heaven forbid, 3,500 miles away and 32 miles in diameter. It makes no difference. You liar. What about eclipses? Well, as I said earlier, we can't just change the sun. We have to scale the moon too. So yes, as long as you divide or multiply by the same number, you'll be fine. So yes, the moon is 0.53 degrees as well, which works out to being 233,400 miles away and 2,159 miles in diameter, as it is about 400 times as small and 400 times as close as the sun. But it would work the same if the sun was 100 times as big and 100 times as far, so that the moon was actually 58,376 miles away and 540 miles wide. Well, then an eclipse would happen because the sun is 100 times as far, so 6,053,900 miles away and 56,000 miles wide. Or the moon could be 14,594 miles away and 135 miles wide, or 864 miles away and 8 miles wide, or even, heaven forbid, 3,567 miles away and 33 miles wide. It could be half that size, 1,729 miles away and 16 miles wide, and then the sun could be double at 3,567 miles and 32 miles wide. Same observation from Earth, of course, because math is reality. Now, some things could help us determine which distance was more likely to be correct. For example, the inverse square law of light that says that given a certain brightness or intensity, it is inversely proportional to the square of the distance. So if we know how bright the moon is, each time we halve our distance, the brightness increases by 4 times. So you see, we can say the moon is 100 lumens, and it doesn't really matter which number we place on there, as the result will be the same. So at 240,000 miles, we have 100 lumens. At 120,000 miles, we have 400 lumens. At 60,000, we have 1,600 lumens. At 30,000, we have 6,400 lumens, and so on and so forth and so on and so forth, till we get down to 1,000 miles distance. When we're 1,000 miles away from the moon, the lumen should be 6,553,000. So if we divide that by the original 100, we see that from 1,000 miles away, the moon would be 65,530 times brighter than it is from Earth. Is that what we saw? Well, here's some photos from Apollo 17 from 800 miles from the moon. And you tell me, is that moon 65,530 times as bright as it is from Earth? Of course not. So one thing or the other isn't true. Either we've never been to the moon, or the moon is far closer. What can't be true is the moon is the distance that they tell us, and that man has been there. Another way that we can determine if the distances we are given are correct is to imagine the sun, I don't know, say it's 1,000 miles away. The sun would take up the entire day sky, correct? Okay, so let's make it now 93 million miles away. Okay, now if you hold a dime out at arm's length, that's about the size of the sun, at 93 million miles or 8 light minutes. So now double that distance. Well, that's now a light 16 minutes. Okay, double it again. Well, now we're at a light half hour. Okay, double that again, and we're now at a light hour, and I doubt you'd be able to see the sun. But let's multiply that by 24, and now, finally, we're at a light day. No chance you would see the sun. But now we still have to multiply that by 365 times more to get to a light year. Think about that, people. How would we see any star, considering no star is that close? Nonsense, mathematical reality. I mean, really, to think that we could see 25 trillion miles. Remember that a trillion seconds is 31,000 years. Think about that and realize that the closest star, other than the sun, is 25 trillion miles. Yole. Now, wait a minute, you yell. Wouldn't the planets have to change as well? Well, of course. Their orbits, sizes, and distance would all be scaled appropriately. Here's an easy way to see it in action. Take these numbers, 0, 3.
Or more accurately, they can just stay the same because we don't actually know them. They're only ever just these ratios in the first place. Equally valid.
6, and start doubling. 12, 24, 56, 108. Okay, now add 4 to each. So 0 becomes 4, 3 becomes 7, 6 becomes 10, 12 becomes 16, 24 becomes 28, 56 becomes 60, and 108 becomes 112. Now divide by 10. So 4 becomes 0.4, 7 becomes 0.7, 10 becomes 1.0, 16 becomes 1.6, 28 becomes 2.8, 60 becomes 6.0, and 111 or 112 becomes 11.2. Now, does that look familiar? Well, it should. 0.4 is Mercury's AU, 0.7 is Venus, 1.0 is Earth, 1.6 is Mars, 2.8 is Ceres, 6.0 is Jupiter, and 11.2 is Saturn. Now, of course, those are approximate numbers as they change based on their distance from the sun, which is changing all the time. So now you have the distances from the sun, 93 million miles times the AU. So Mercury is 37.2 million, Venus is 65.1 million, Earth is 93 million, Mars is 148.8 million, Jupiter is 558 million, and Saturn's about a billion. Of course, you can then figure out exactly what their distance from Earth is, with Mercury being 56 million, Venus being 26 million, Mars being 34 million, and Jupiter being 367 million miles from Earth. But what if 1 AU is actually 3,567 miles, not 93 million? Well, 3,567 is to 93 million as 1 is to 26,072. So scale it all by 1 26,072nd, or I'm not really sure. Then you can even figure out the distance from the Earth. So Mercury is 2,147 miles, Venus is 997, Mars is 1,304, all miles from Earth. Now wait, wouldn't they need to be smaller? And, well, of course, scaling and variance. So Mercury is actually 2,147 miles away, and with its angular size, it would come out to 0.11 miles, so that would be 603 feet in diameter. And Venus at 997 miles from Earth would have a 0.28 mile diameter, or 1,520 feet. And Jupiter would be 14,076 miles away and 3.40 miles wide. And we can check our work as well, because 3.4 miles is 1/10 of the sun size at 33 miles in diameter, which matches the current model with Jupiter 84,000 miles wide and the sun 860,000 miles wide. No, you cry. Give me my Santa back. Wouldn't gravity be different? Well, would it? Well, here's the thing. Whatever amount of gravity has been given to the Earth or the sun or any of the other planets is based off mass. Well, we can easily just change the mass of the sun. Who is weighing it? The answer is no one. And we can change the mass of the Earth. Who is weighing it? Cavendish in his shed? Give me a break. And quit it with your religious stories. It's becoming silly.
Excellently put from the flat earther formerly known as Jared. You guys got questions, comments so far?
No, just that the scale and variance thing was such a huge concept for me as well. Like knowing that it just scales
Yeah, it was
off
foundational,
of a scaling
foundational for me.
factor.
Yeah.
Yeah, it's just like knowing that it removes all physical meaning to what they've done with the ratios of pi and periodicity.
I
Yep.
just wanted to comment. Sorry, I just quick comment. Jaron explained all that so beautifully, like easy to understand, right? I can't understand how he went from this to whatever, but whatever.
I know.
Yeah.
I've only ever heard this side of him, to be honest. So this is what I'm gonna go with.
That's because I miss the old Jaren. Yeah.
It's money. Money.
But so that scaling invariance thing, like that explains this right here, right? So when they're saying, "Oh, look, we know that we're look at all these scientist lads making genuine effort at guesstimating the size of the distance between the Earth and the Sun, also known as the AU, through the same rigorous process, getting further, like closer and closer until we got it." That's what they're portraying here. But if we know this formula here, we're really just going to change two of these because we know that it's actually 0.53 degrees, and the only thing we ever observe is 0.53. So we plug that in, and then we play with the other two until we find a value that fits. But this is the angular size formula as it pertains to astronomy, and it just means, in this instance, we're defining it as theta, which is just 2 times the arctan of the size, or the diameter, over 2 times the distance. And this is how you would visualize it. And you can, of course, algebraically rearrange this to solve for any one of these, which is what we're going to do next. So when they say we know that the sun is 93 million miles away, or 160,000 kilometers, we just use 2 times arctan over the diameter over 2 times the distance, and we figure that out. We plug this in. We know what our angular size is. We solve for all the rest of it. We can just say, hey, we'll plug it in, and we know it's 862,000 miles. Okay, we're going to use that one, and we come out with exactly the same. So this is the formula that they would use to change the values to get different distances at the end. This one happens to work out for 93 million miles, but applying the same principle in this formula over here, you can get all of these distances by doing just this algebraic shuffle, plugging in a different diameter and a different distance, a different diameter, a distant distance, and then this will just give you tuples or cooperative pairs of data that cooperatively work together that do covariantly scale. And again, that's a super important part of it. Now, you can also rearrange it roughly to get what we went over for a similar position. So if we're going to base everything off angular size, then it also works, as Jaron likely pointed out, for a sun that's 32 miles across and about 3,500 miles away. And that's just, as he said, because math is reality. So the vast majority of globular evidence is based around this. This is what you hear people argue. Angular size. This is what I think Alan and I always argue against. This is the position that we always take. We always just say, well, it's always based on an angular size, and it doesn't matter because it can be covariantly scaled to any distance, and that distance at the end really has no inherent meaning. Its only meaning is its relative ratio to the rest of the components in the system. And that's really the important takeaway. Now, knowing all that, I think we should watch another video of a Astronomy 101 college course, which would be about as far as the people who you're arguing this will have gone, on how they actually derive any of this stuff. So let's see here. Yeah, Astronomy 101. I'll put it in a little bit quick speed. We'll watch it 1.25. It's about 15 minutes. I'm going to skip forward a little bit in a couple parts. But I think it's important to watch it in this context, because if I were to try to steelman it and show you the math, that would always be wrong. This is what the Cell Theo has taught me. Anything that we say is wrong. So let's play it from their side for the next 8 minutes, and we'll go through the actual math of how they turn these well-established and well-known ratios into so-called exact empirical measurements.
One thing Kepler did not tell us was the absolute size of the solar system. He tells us the relative size. We could take the planet Mars, for example. We know its period is such and such. We plug it into Kepler's third law, and out we get the semi-major axis in astronomical units. We don't know how big an astronomical unit is. We just know it's the distance between the sun and the Earth, but we don't know what that distance is in something meaningful, like meters or kilometers. So we can say that Mars' semi-major axis is 1.6 times that of Earth, Jupiter 5.2 times that of Earth, or whatever the numbers happen to be. We understand the relative scales and distances and spacings of the planets, but we don't know the scale absolutely. And to do that, we have to actually measure one astronomical unit, the Sun-Earth distance. So we're going to take an aside here and talk about 2 ways in which this was done. One, very early on, using parallax measurements of Venus, and one, a more modern-day solution from the 20th century, where we actually send radio waves out there, with the radio waves bounce off of Venus and come back, and we measure time of flight. So again, Kepler gave us the relative size of the solar system. Now we're going to figure out the absolute size. And to do this, we must measure 1 AU. So let's take the case of Venus. It's the planet that gets closest to Earth. And here it's drawn in that configuration of closest approach. We have Venus's orbit, which is at 0.73 astronomical units. Again, we just figured that out by measuring its period. How long does it take to go around the sun? Stick it into Kepler's third law. Kepler's third law tells us it's at 0.73 astronomical units. Kepler's law tells us that we're at 1 astronomical unit by definition. And so sometimes Venus is very far away from us, sometimes it's close. Here it is at closest approach. And at closest approach, it's 1 AU minus 0.73 AU, so 0.27 AU. At different positions in its orbit, it would be different numbers of AU, but let's consider this configuration, because it's kind of the easiest to deal with mathematically. So if there's some way that we can measure the distance between Earth and Venus at closest approach in actual units, something like meters or kilometers, then we can figure out how many meters or kilometers are in 1 astronomical unit, and then we know the actual absolute physical distance to everything else orbiting the sun, because we already know those distances in astronomical units. Okay, method 1 is parallax, and we'll get to work an example of a parallax calculation now. Simultaneously, it should appear around different stars. There should be, and we're looking at Venus, and we'll now suppose that that gray object, instead of being the supernova, the comet that we talked about before, or the moon as it's referred to in the textbook, we'll presume this is Venus. And if we look at Venus from one side of the Earth, it should appear around a certain set of stars, distant background stars. And if we look at Venus from the other side of the Earth simultaneously, it should appear around different stars. There should be a shift. And we're going to go through this geometry. Now, this is a geometry that we'll encounter over and over again in this course and in the lab. You can use this for many different things. You can use it to measure angular sizes of objects. In lab 2 that you're approaching, we'll use it to measure the size of the Earth, all sorts of things. So this
we use it for all sorts of things, for everything, actually.
You'll see it double. So here's the basic idea. What we have here on the left is Earth, and here are the 2 points of observation, one on one side of the planet, one on the other side of the planet.
So this is the main principle put forth in the parallax measurement that we're going to go through really quickly in detail. But just know that this is just ratios of a circle with no inherent meaning, just like Eratosthenes' measurement with his measurement of an arc angle so that he knew the distance between Alexandria and Syene. This has no actual meaning until you put value over here. So how do we get value into this equation? Well, we know the radius of Earth, don't we? And what is this? 2 times, what is this, the diameter? There we go. So if we look at the sun and we measure shadow angles according to Eratosthenes and we plug in distances that we've already known through Bamantus, then behold, we have, quote, measured the radius, and then we behold, know the baseline distance of this Earth so that we can then compute all the rest of the distances in the known solar system. And again, I just want to call out that all of this is now dependent upon the validation of a radius, which is taken from sun angles and shadows and only ever gathered from looking directly at the sun.
The distance between them, we call that the baseline. That's the distance between the observing points. A class ago, we did the experiment with the finger, where you put your finger in front of your face and close one eye, and then shift to the other eye. Your 2 eyes, the distance between your eyes is the baseline in that example. And you're looking at your finger, and that's the distant object.
Isn't the other part of that too, you have to use units of measurement derived from a system that already assumes the radius? So like you already have to have a value to even have a unit of measurement to apply to this?
Yeah, it's also part of a meter, so it's already ratioing itself against proportionate terrestrial baby meridians, if you will. So yeah, there's also that layer to it where it will always come back to itself. But like, so it's better to keep those because there's 2 separate instances of it happening. They're not like layered up. So this is happening and then the other thing is happening and it's twice as bad. It's not like bad squared, you know? Like, this one is separate because they have to assume the radius for this one over here. And then they're also assuming the radius to measure things in, 1/10,000,000th of a terrestrial meridian.
That's so crazy. It's like they're doing another central angle based off of another central angle that they started with to get that.
Well, we set out by saying we want to know exactly how big 1 astronomical unit is in something useful like meters or kilometers. That's what the professor said. We need to know it in meters. So how do we know it? Well, we'll set up this fancy other basic geometry principle, and we'll know that this length has to be, equal to this circumference, and we'll use 2 pi r. But it all is just going to be ratios of a circle. Like you're only going to have 2 pi r in circle measurements and angles unless you plug in a real, like the whole point of this depends on a real world distance. And the only thing that they know, they just kind of slide in here. Of course, they don't tell you how they get it. They just plug this in terms of scientific notation and meters later. So you won't even recognize it, but it's 2 times it's the diameter of Earth, right? If you just went, this is the radius and this is the radius twice. That's what the diameter is. So that's how they get that. And they don't tell you how they get that. We all know the radius is only ever measured via Eratosthenes and sun angles and looking at shadows and assuming other known distances.
So in this, we're measuring the distance to Venus. So the gray dot over here, consider that on Venus. Nothing's to scale. If it was to scale, the angle would be very, very small. It would be hard to fit all the numbers and letters on here, the arrows. But imagine
whatever.
sides of the Earth. So if we're looking from the bottom part here in this figure, Venus would appear over in this part of the sky. They're background stars, and it would appear to be near them. If we're looking at Venus from here, at the exact same time, it will appear to be in a different part of the sky. It will appear to be over here compared to background stars. And we can measure that angular shift. And we're going to call that angular shift theta. And so I'll write this down here. Theta is the angular shift as observed from one side of the baseline to the other. In this case, we're talking Earth baseline. And for Venus, it's about 1 arc minute, approximately 1 arc minute. And 1 arc minute is what fraction of a degree? 60th, yeah, 1/60th of a degree. And if you remember, 1 arc minute is about as good as you can do without a telescope. So once you introduce the telescope, this is a very easy thing to measure. Stars, when you look at a picture and there's stars in the picture, the stars tend to be blurred out to scale of 1 arc second due to atmospheric blurring effects, the atmosphere shifting around and blurring our image. 1 arc second is a 60th of an arc minute. So an arc minute is like 60 stars across if you line them up side by side. It's a very easy thing to measure once you have a telescope. So this was a very easy measurement, and that's the observable, but we want to turn this into a distance. Well, the concept is, imagine drawing a giant circle centered on Venus.
Kind of sounded like Jesse a little bit there to me. I didn't want to notice.
The figure comes back around and back here. So you can think of this as an angle as a fraction of 360, or a piece of the circumference of this big circle as a fraction of the whole circumference. You know, in any circle, you have 360 degrees. This angular shift is some fraction of a full 360 degrees, theta over 360. And that has to be the same fraction as this distance, the baseline, divided by the whole circumference, the big circle.
Yeah,
think of it as a giant pie, and you're taking a little sliver of pie. How much pie are you eating? You can measure it in angle. That angle is some fraction of 360 degrees. That's the fraction of the pie that you took. Or you can.
Yeah, that is why he said he didn't want to draw it to scale. I think he said it would look
1 over 21,600. Go, buddy, you go.
Measure it out on the circumference of the pie, the crust. I took 2 inches of crust. Maybe there are 20 inches going around. I took 1/10 the pie. And those have to be the same number. Okay, so let's write it down. In fact, it's written up there, but also right on the dot cam. In fact, I'll do it on a new page. Make some room for the computation. So the angular shift, which is what we measured, divided by 360, is going to be equal to the baseline of observation divided by the circumference of the giant circle. So what's the equation for circumference? Circumference of a circle is equal to 2 pi times the...
Okay, it does this, and it's really annoying. So I'm just going to skip it until we go over here.
Well, let's work at diameter of the Earth. And it's about 1.3 times 10 to the 4 kilometers divided by 2 pi distance.
Did you see how he just snuck that in there? He's like, oh, here's this already previously known, scientifically, empirically modified, measured, confirmed, double known distance, put it at the top numerator there. And the thing we're going to solve for on the bottom using the thing that we just supplied on the top. Just saying.
And distance is what we want to know. Well, let's take this, you stick it into a calculator, and you do that, you're going to get a very small number. 1/60th divided by 360 comes out to 4.6 times 10 to the minus 5, and there's no unit, it's dimensionless, the degrees have canceled out. And over here, if we divide 2 pi into this number, we get about 2.1 times 10 to the 3 kilometers divided by the distance between Earth and Venus at closest approach. Now, if you're farther away, you're going to get a different angular shift, and so this would be a different number as well. That closest approach, that's the angular shift, and so that's the distance closest approach. Now, to solve this, we need to solve for distance. So let's get distance by itself, and I'll just go through the steps here. We're going to multiply both sides by distance, and divide both sides by this small number right here, 4.6 times 10 to the minus 5. 4.6 times 10 to the minus 5. The reason we're doing this is these will cancel out, giving us a distance by itself. Now on this side, distance cancels out. All make sense so far? Just a little bit of algebra, practice in solving an equation. So we get distance is equal to 2.1 times 10 to the 3 kilometers divided by 4.6 times 10 to the minus 5. You plug that into a calculator and you get about 4.5 times 10 to the 7 kilometers. So that's the distance to Venus at closest approach. You can measure it using the parallax technique. Now, why are we doing this other than to have an example of a parallax calculation? Well, we want to know how big the astronomical unit is in something that we're familiar with. And kilometers, we all know what a kilometer is. So let's go to the next level here and let's solve for 1 AU. Now, at closest approach, we already said at closest approach, Venus is approximately 0.3 astronomical units from Earth.
Back to Kepler, where we started,
AU
get our ratio.
Approximately 4.5 times 10 to the 7 kilometers. So if we want to know how many kilometers are in 1 astronomical unit, we'll divide both sides by 0.3. Over here we get 1 AU is equal to, do the math, and it's 1.5 times 10 to the 8 kilometers.
1.5 million-ish kilometers, right?
It's pretty big. I mean, that's a huge number of kilometers, 1.5 times 10 to the 8. And it doesn't really matter if it's big or small. The point is we need
the scientific notation is definitely rusty.
Distances to everything and the real scale and size of the solar system. Now that we know how far Earth is from the sun, since we know all the other planets, their distances from the sun in AU, we now know them in physically meaningful, like a kilometer.
Now we scientifically know everything, all the distances in the world. Do you guys get that? We know it. We can follow it. Good. We know everything.
It is known.
Okay, that's one way to do it. The other way I'll mention briefly, and you'll work an example of this in a later homework, so it's good to get the example now. It's a little bit easier to do mathematically, but I want to show you how it's been done for centuries. Then you enter the 20th century and you have technique number 2, which is radar ranging. After World War II, this was possible.
Oh, yay! Oh, yay! Here comes the radiation stuff. I'm going to send some EMF out there. Oh, boy.
Nope, skipping that. Gonna put that on pause for right now. We're gonna talk about that first part for a second, and then we're gonna go into radar ranging right after this. I definitely wanted to pause it there. Right when you got excited, wanted to let it play. No, so here's the math that he just did. Right. So again, we're doing basic parts of your job, basic geometry, parts of the circle, relative comparisons. What we're doing is we take this known. We need this known diameter of Earth now. Over here, what's it? Whatever this is twice 6,200 kilometers or whatever. The radius of Earth in kilometers times 2 is roughly what you have this over here. So he used this whole formula as like, we're going to determine something for real that has a real life value by determining this. We're going to find this distance down here. This is what we're going to find. But quickly, we're going to put in this definitely already known distance of this radius value for the thing with which we're going to define the coordinate system defined in a percentage of terrestrial meridian itself. Anyway, so the math, makes sense. If a glober was in a debate with you and he did this in pen and paper in front of you to show you how wrong you are, like the only way I think that you because this is, basic algebra, replacement, parts of a circle, 2 pi r. I mean, basic stuff. I don't think you're gonna attack it that way. However, the significance and the meaning of over here is where you're gonna get it, because falsifying the radius value, of course, on the surface, and then using that as a standard candle to base everything else. I would argue that the AU could be like a proportionate unit of actual Earth radii. It's just the proportion. It's just a certain portion of radii that they then use to do other stuff. So this was the main method that they use again, and they just plug in a known radius, just like Eratosthenes. The way he got the circumference was knowing exactly the distance between Alexandria and Syene on the graticule, and that's how we got the bigger, larger value on the graticule. That's how Eratosthenes did it. It was almost exactly the same way over here. So, again, if we look at, first of all, whenever we mention parallax comparison, I think we should go through this over here. So this is the diagram that you always see. This is the diagram that you never see. Just saying, if Earth was geocentric, parallax would appear identical, the same. The angles would be identical. If you don't notice it, it looks a lot like this, right? And the angle we were just looking at could fit it over nicely. And of course, the angle we were just looking at could fit over here nicely. So the significance of that real quick is that they're identical. It's as if centered from Earth, but the reference line is geocentric, and all of the angles are exactly the same. So no matter which one is fixed, the apparent movement of the star relative to Earth's distant background or whatever, as they put it, is identical. You're just relabeling which one you like better. So that's the basic argument for parallax and how they use ratios of Kepler's law with a supplied known value to arbitrarily define everything else by relative known to that known value. And there it is in the math right there. So moving on, we can do the second part of where they actually claim to measure the distance to the sun using radio waves, and we're going to go through some papers, some Toon papers, some other papers, some NASA papers, and anyone who has more expertise in radio waves and ham radios or whatever, feel free to pipe in for sure. Stone, looking at you. All right, we're going to get back to this part. Let's see.
Well, you took, or you can measure it out on the circular baseline of observation divided by the distance between Earth and Venus at closest. So speed times time.
Here we go.
And the distance that we're traveling is to Venus and back, so that's 0.6 astronomical units. Again, I'm rounding off. The speed of light in kilometers per second is what? To the fifth, that's right, kilometers per second. And then all you have to do to measure what 1 astronomical unit is wait. So they send the pulse out. If the solar system is big, now they kind of knew what the answer was. From the parallax measurements, we know how big an astronomical unit is. But if we had no idea, we'd send this pulse of radio waves out, and if the solar system's huge, you might have to wait hours for it to come back. If it's really small, you might have to wait seconds for it to come back. It is what it is. It takes about 300 seconds for it to come back, rounding off. It's about 5 minutes. So it shows you how far away it is. Communication round-trip time scale to Venus, about 5 minutes. The seconds cancel. So we have 0.6 AU is equal to a certain number of kilometers. Let's see, that would be 9 times 10 to the 7 kilometers. Divide both sides by 0.6. You get 1 AU is equal to, again, of course, you come up with the same result, 1.5 times 10 to the 8 kilometers. So those are the two primary ways we know how big an astronomical unit is, and consequently how big the solar system is. Questions about that?
Several. What do you guys think?
Seems pretty straightforward.
I want what he's been smoking.
Did he just throw in that one equation that said this is it and didn't really say why?
Well, so the thing is, D equals V times T is pretty standard, and if I was going to argue against that, I'd find myself a better position, right? So I don't know. Like, D equals V times T, I was looking into this, and I was like, well, shit. Where do I... What he just presented seems pretty sound. You guys disagree? Like, where would you poke holes in it? Does anybody know? You disagree with the speed of light?
Same places.
So where I would go
Depends
is
on what the medium, presupposing the medium that the light's going through, perhaps.
that's a very good point. Assuming the speed of light in a vacuum doesn't seem proportionate to whatever we're trying to measure in any real life circumstance, definitely true. But where I went to try to attack it was he was like, hey, we needed this signal and we need it to be like it's exactly this many seconds. And I went, oh well, how did you know?
5 minutes.
How did you know it was exactly that many seconds? And that is the story that we're gonna go into now, lads and ladettes. That's gonna be super fun. So right here we have our first paper, and it's, of course, the best proof you'll ever get, mctoon.net. Here's the link. Radar echoes from the sun. He cites it all the time. He holds up his website, and it's from 1960 from these dudes, Eichelman, Barth, and Gallagher. And they go on to say that they definitely for sure bounced radio waves off the moon, and they got a longest usable echo time within 12 minutes or whatever sums. But to understand what this means is they're using solar radii to get a periodicity to amounts to a series of noise. Why is it noise? Well, they have a super sensitive receiver, and no one's ever done this before, and they don't know what the hell they're looking at. But they've set up this this receiver over here, and in between all the noise that they know they're getting, they got this super identifiable echo, which happens to resemble all the noise before and after and during it, but is definitely an echo because it coincided with the previously mentioned solar radii of the measured solar periodicity. And that's how we know for sure that it's not a noise burst that appeared before and after it, but is definitely itself a return. So this is actually the coolest graph I've ever seen, because it actually does the courtesy of pointing, oh, here's the useless noise data, and that's nothing, useless noise data, useless noise data, not useless noise data, useless noise data, useless noise data, useless noise. You can see that all.
But Shane, come on, right between the 3 and the 0. Look how pointy that little piece of dotted.
Well, yeah, and we predicted that it
So
would be this
pointy.
narrow. Yeah.
Oh man, but like, hey, check this beautiful diagrammatic lesson we're looking at in Figure 2. When over on the far left on the y-axis, it merely says amplitude. Okay, that's so scientific.
Might as well call it y.
Absolutely zero magnitude indicated. Like, what kind of amplitude are we looking at here? You know, as in dirt, sleight of hand.
Yeah, within the paper they go into this, like how ridiculously specific this is and how very much identical to all the other noise this actually appears. And in the graph, to be fair, they represent it accurately. It looks just like all the other noise, but then they just say that it isn't, and that it's definitely important. Now, there's also other examples where we'll find where they get previously fake signals, false detections, mistakes were made, as they say. 2 signals read as 1, which definitely wasn't a radar return, and a couple other whoopsies that we'll go over, and which is just the historical progress and how we got to the absolute certitude of the number that we know today, to be confirmed as we started off.
You listen to enough. Yeah, sorry. You listen to enough noise, you're gonna hear whatever you want to hear, I guess.
Like if you listen intently to static with just the same 8 words that you want to hear playing on repeat in your head, there's gonna come a day where you're gonna hear those 8 words in the static. It's just a fact. I think that's what he's saying. So some of the other papers that we were going through, as we leave McToon's reference behind, is this is a NASA paper, To See the Unseen, a history of planetary radar astronomy from the dude Budrika. Now, as Alan pointed out, this is one of our dudes who literally was writing his thesis on depending on getting this echo return based on all the stuff that he was contextualizing and putting forth as his hypothesis. So he for damn sure was going to find this echo no matter what, because it turns out he did get his thesis, right? So this one's kind of long and reads like a book, so we're just going to go with a little summary of what this dude did, and we'll pick it up right here. He made an observatory prototype. He was the first prototype for planetary radar using maser amplifiers and long-time integrations to detect Venus echoes. Some other dude in Bank built upon that, actually corroborated his results super quick, and then they had a large 76 radio telescope, and they said exactly the same. We got your back, bro. Soon thereafter, 2 years later, our boys at JPL, Jet Propulsion Laboratory over at NASA, using their also super duper highly sensitive radar at Goldstone, achieved the first unambiguous real-time detection of Venus in 61. Now, this is the big one. The big one, as they say. After a couple false positives, this is definitely the one that they wrote down in history that they prepared it all for. So the results then were, erroneous by a little bit. They got to make it appear real, so they had this slight correction thing happen almost immediately thereafter by the Soviets, give them a little check. And then they said, actually, you're wrong. We measured it a little bit differently so that you give the appearance of the two sides fighting and that you get the actual agreement on the AU, which they then go and agree with at the International Astronomical Union. So moving right along, still talking about this base paper. Again, the guy who wrote the thesis for it depended on returning the thesis. But we'll get back to actually how that plays into what we're saying. Here's the paper to reference if anyone wants to go check it out. Taking a quick look at the math that we just looked at for radar ranging. So this is what D equals V times T, so distance, velocity, and time. And we've already went over how we know distance, like the AU. We know this is a ratio of the AU that we just solved for later. We don't use it as anything more than this ratio as we multiply it by a final result to get what we're getting for. So the only things we can possibly attack in this example would be the speed of light, which is going to end up over here in meters per second, or the time that they get this radar bounce signal. And I don't know about, I think we accept the speed of light, not so much as a speed, but as a rate of induction that is measurable and is, quantifiable in a vacuum and is repeatable and is, dependable. So I don't think that we want to attack the speed of light. If anyone disagrees, let me know. Happy to attack that bitch if you think we can. But over here, this 300 seconds is where they definitely said they got a radar return, and this is the only part of the equation that we're going to be able to critique relative to this, because we already went over how they established this, and we're not going to attack this. That leaves literally only the time. So how did they get the time? We'll figure that out. So here's how the little breakdown of the math. Here's the variables lined up. Distance equals velocity times time. They use this, the distance AU measurement, approximate speed of light in meters per second, the time, like I said, the one that we're going to attack, and then they use this calculate, which is just the actual derived for the AU. Another thing is that it's a one-way distance that they end up deriving and then using it to just divide what they use as a two-way, because they know it goes there and comes back, divided by 2, and that's all they ever get for this justification. And it is dependent heavily on the speed of light in a vacuum. Now, do they shoot the radar entirely through a vacuum if they say it's 93 million miles? Of course not. That's crazy. That's crazy. Some of the biggest critiques, though, I lined up over here, and we saw a lot of the same stuff with LIGO. I think there's a lot of comparisons to how LIGO is used to detect gravitational waves through a complicated series of neural network layers and interfaces that would interpolate said data noise through interpretive networks stacked on top of each other until they would refine said noise to actually resemble the signal they were looking for in the first place, according to the pre-designed templates. That's
Convoluted
the real process. There you go. Yeah. That's the real process of how they actually scientifically detected gravitational waves at LIGO. And they're doing the same thing with these radar bounce signals from the sun with these super sensitive radars. So what they're saying is, subject to noise, signal processing artifacts, other assumptions about the source and the medium. This is the main critique I think that I have against it. Not to mention, when they do the test, they have all sorts of false positive echoes, bounces, unknown solar noise bursts, things that make it difficult to definitively attribute whatever you get as your tiny signal as the actual return of the signal within the time frame that you're looking for. So,
which made it so much easier to punk them.
well, they had a pretty good idea of how long the signal would have to take for all the rest of their stuff to be true. So they were, as this time period would elapse, they listened super hard to make sure they didn't miss it,
Dude, they listened so hard they didn't include any magnitude on their amplitude, so you don't even think about it. Like, how big was that peak on that cone? Zero. It's just noise.
Certainty they're going to find this peak within this time frame. I'm guaranteeing you beforehand it's going to be within the 5 seconds, whatever that they need to have this work out. But they don't know that yet. They're going to pretend that that's not happening. So the other thing is that even though it's pioneering and awesome, it's not really independently verifiable so far with contemporary because of the high precision requirements, the ridiculous amount of interpretation after the fact with the data processing, the actual corrections that you get for any sort of signal, all that stuff sort of plays into it. So that would be where I would critique it. So
$380 million in hardware.
Yeah, like a super sensitive material. We'll go into the pictures of what you would need if you wanted to like rig this up in your backyard. You need like a couple acres and a couple $1 million, like seven destroyers worth of steel or whatever. The thing is huge. But if you wanted to, I mean, technically you could. It's just that nobody ever has since. So they needed 300 seconds. Notice that they got exactly 300 seconds through their highly sensitive receivers. They knew that it was a round trip, and this actually also relies on the precise clock systems, often atomic clocks, calibrated transmission reception in the observatory. So we know that there's probably some time dilation that's happening within that relativistic time, within that relativistic time dilation within that atomic clock that actually makes this all work out in the end.
Dude, I wish there was some relativistic time dilation in a stationary clock.
But that's how they know that this is definitely 300 seconds. So this is double confirming the time that they definitely got the signal bouncing back from Venus to verify its distance. moving right along. So again, there's just other critiques, some systematic error, other things that could possibly go wrong. And this, of course, anything with like, say, if the speed of light wasn't c, but as we know it was c plus v relative to its distance and speed of velocity within a relative medium, that would inherently and literally change everything about what we just said and did and learned, and it would change it drastically. And even though we indirectly know that the speed of light is c plus v through other independent corroborative research, we will just ignore that for now because that would inherently break this entire system.
So,
here's one of the
so basically, to make it work with the established vacuum speed, though, and the time frame that they would need to propagate over that distance and return, they just look for noise at that interval and was like, "Look, there's this noise is different from the noise previous." Because, if I remember correctly, one of the things they did to try and say that they verified it was letting it drift on purpose or whatever. So like they would track Venus for like 5 minutes or something, and then they would let it drift, and then they said that the noise difference from what they were getting when they were tracking Venus was different from when they weren't tracking Venus. But as we just looked at from their non-magnitude amplitude graph, we have no idea what the actual difference is between the static noise and the noise that was measured in the time frame for the confirmation of the distance to Venus.
Yeah, to be fair, that the first graph was from a different paper, but yeah, they also had no graph in that paper. I think the second one that we were talking about, but they didn't quantify it very well. And you nailed it when you first said, so all they have to do is look super hard during the known interval by which they think they'd have to get a return to, which would validate the rest of the thing. And that's all they had to do. When presented with constant noise in, say, sinusoidal intervals and peaks and valleys, and you got to look for a specific peak and valley, and you say, hey, in 5 seconds, let me know if you see that peak and valley, okay? And you go, okay, 5, 4, 3, 2, okay, did you see it yet? Did you see it? Yeah, I think I see it. Did you? Okay, stop. Everything, we got it. You know what? We got it. Is that it? Is that the peak and valley that you were looking for? Is this your card? Yes. Okay, that's it. Pack it up. We're going home. That would be how easy it would be to do one of these things, and then just present some data with all the rate of returns from all the data that you collected from your super sensitive, unparalleled, receiver, etc. But buried within all that, we have another parallel to LIGO, and this is a chapter called "We Were Wrong" from the paper "To See the Unseen: A History of Planetary Radar Astronomy." Technology and culture that we went over before, and this is the DOI for it. And this is funny because it's like, actually, we were really embarrassed because we messed up. We had the wrong value. We had the wrong signal. It was way over here. It wasn't that it was over here and was way over there. It was that really embarrassing moment. So he says it determined that when they were looking real hard during this specific interval when they needed this return, they thought that they found one, but really it was two different signals that they just meshed together that arrived distinctly 2.2 milliseconds apart. Remember, they're using super sensitive equipment. This distinction at this level with this specificity is nothing. They can do more than that. This is a big distance for them. And what they said was, we told the press we might have saved ourselves some embarrassment, but that's in hindsight. The two pulses arrived 2.2 milliseconds apart. We just turned our backs on it, meaning we looked at it, we noticed it, we turned around and we said, fuck it, we're going to tell everyone we did it anyway. We did a little wishful thinking, and we said, that's the same pulse. I just put them together. I ignored the difference, and I sat them one on top of the other. And boom, radar return from Venus, distinctly confirming the distance within the time interval variable to be compatible with the ratio of the astronomical unit and the speed of light. And onward we go. Questions so far?
So what came about that happened?
What happened? So they got the super sensitive equipment to receive this super sensitive signal back within a time, and then they did.
Did they change anything? Did they
No.
change nothing?
Yeah. Well, so what happened after this is that they eventually detected one that was real in exactly the same circumstances, but this one was real. So if you're familiar with the story of LIGO, what happened with them was exactly the same. There was some fake noise that some of the people interjected knowingly into the system that would resemble an actual gravitational wave, and when their system detected it, they were like, yay, congratulations, you guys passed
Like-
the test that we set up for you to detect the wave. And they're like, oh, but we told the press it was real. And they were like, no, we definitely put it there. And then they waited like a month, and then they detected another symbol, and they were like, dude, this one's totally real. You guys got it. And that was it. That was the detected for the gravitational wave. So what happened here was after this first false positive, when they told everyone that it was fake, they actually immediately detected the perfect signal within 5 seconds, down to the third or the 100th degree of specificity. The third decimal was exactly 300 seconds to unparalleled specificity.
Well, that's convenient.
Yep. Makes total sense. No questions.
It reminds me of a common it's like a common tactic they use. I mean, it sounds like you're saying they're presupposing it to a model they have. So it reminds me of like geodetic surveying or something, where they take a bunch of measurements or like all the noise that's coming in, and they selectively choose the one, focus in on that, the area it has to be, and make it work, basically.
Yep. That's what they're doing. They're really good at it. They have a predetermined model. They take everything else, they apply it to that. Brian?
So is the point that they got these peaks thought matched what they expected, but it turned out that those peaks weren't actually the signal that they got, so they had to go and do a retroactive correction. But then the next time they actually measured it for real in the same exact spot as the fake peak, it was just a real peak this time.
Yes, exactly that. It's exactly how it happened. That is the actual history. Nailed it. Didn't even read the book, dude. That's crazy, Piers.
I heard
That's
that it's
crazy.
possible to ascertain all the necessary information in any document by just reading the abstract. I don't know if that's true or not, but I've heard that's a very possible way to absorb all the necessary information in a document is just read the abstract.
I've heard you don't even have to glance at the abstract. You can just know through through a power of the being arguing against a flat earther that whatever they're presenting is wrong, and then you don't have to look at it to know that how wrong they are. I think that's
They're reading
probably
the title.
Well, that
Yeah, not even-
requires special
Yeah, I think
Benny
we learned-
Jesuit training to just have the inner know. It's called the inner knowing of wrongness, and they just know at a glance that everything you said was full DS.
Yep. So after that, one of the papers citing one of the
Yeah, I
other
learned that
detectives.
yesterday. Sorry, go ahead.
You learned, dude?
He didn't learn anything. He said continue.
So this is another paper that I thought was really interesting. I had a lot of fun with it. This is one, right? So it's from NASA, JPL, Jet Propulsion Laboratory, California Institute of Technology, et cetera, back 2003. Summing it up real quick, some of the things we're going to focus on is what this actually calls out is some interesting relationships between what they call astronomical constants, or a select group of fundamental constants, including solar parallax, Earth-Moon mass ratio, the speed of light, radius, and others. Meaning, hey, we have a bunch of constants that independently, totally, definitely work, but seem to super duper work with each other and have this weird relationship with each other where they always kind of equal and point to each other. That's what we're going to find out, which reading in this paper, I thought was interesting because that's what I've been arguing with a covariantly scaled, internally consistent network the whole time. That's what you would have. That's what it would be. So again, so he says the constants have several important.
I'm sorry.
Go ahead, dude.
Could you go back just 1 second? Because that stood out to me, what you just said about the relationships. So are you saying that? No, the previous slide.
Yeah, the other one's better though for what we're going to show. Like this is where they actually say it. Say, hey, the fundamental constants of Earth consisting of the elements of its orbit, mass, size, shape, orientation, inner constitution, speed of light are the system of astronomical constants. And it's called a system because it's a model of Earth and its motions. All interpretations depend on this model, et cetera, et cetera, et cetera. And he says, hey, there's some theoretical relationships I noticed that may be profitably revised, which we can use with inclusion of these new radar measurements. And it will be shown that, wait, hold on, wait a second, over here. They said, yeah, it's the many theoretical relationships, including the constants, are necessarily systematically related. and that an ideal system of fundamental constants should be one in which these theoretical relations were satisfied rigorously, while the adopted value of each individual constant agree with its observed value within the limits of the uncertainty of the latter. And it says this ideal has never been realized even today.
That's my favorite quote.
Meaning none of this shit is independently verifiable. The value of all of these are actually interrelated on each other. How interesting is that?
And it all started with a big R, or like the
We're
radius.
down to the unit radii, so that's what I'm arguing. Yeah.
Wait, why would they say this? They're acknowledging that there's these constants, right? Like the motion, the mass, the size, the shape, the tilt, the rotation, that make up the velocity of light. And he's saying ideally we would want these things and the relationships between them to be like empirically measured.
Yeah, in ideal world, we
Right.
would want that. Like that would be sweet for science lads, That's what he's saying. Like wishful thinking.
While the adopted value agreed with its observed value within the limits of the uncertainty of the observed value, but that hasn't happened.
Yep.
Well,
The individual
so they're saying it hasn't happened that the values they use agree with the values they observe?
You said that you can't independently verify any of these. You can only verify them when in relation to each other. That's what he's saying. Which is what I'm saying. Which is what Jaron was saying.
Which is
Right.
100% uncertainty.
Right, which means they actually have no real empirical value no matter what you do. They're only ever defined in relation to each other. The ratios.
0 sigma.
Crazy, right?
0 sigma is one of the lowest sigmas you can get, I heard, in statistical analysis.
I would vote for a negative value to be applied to this entire thing here.
Negative siggies, dude? Is that legal? Can we do that, guys?
Yeah, we can now.
Keeping all that in mind, here's a bunch of people who did the exact same super rigorous test that we just went over using all of our independently internal heat system measurements to come up with all the same stuff that we just said. When they detected their radar signal within their 5-second window with also super duper accuracy. And here's some lads who did it with some less than stellar accuracy, but they all did the same method.
So for 5 seconds, Venus transited in front of the sun.
Nope. Nah, this is just sending radar to Venus and then getting the bounce back time that it takes for it to, the time of flight to go to Venus and back. They're saying that this is the distance covered from that time of flight.
They're essentially saying it based on the AU and the approximate relationship of the ratios of Kepler put forth by the solar system description, that on its, I think, perihelion or whatever, whenever it's closest, they're going to take this and they're going to bounce it from here to there when it's theoretically closest. That's what most of these papers seek to do. And then they know that they have a specific time range that they know based on the speed of light. They know how long that radio signal has to take before it gets back. So during that time frame, say within 5 seconds, after 5 seconds elapses, they look super duper hard at all that noise, which looks a lot like the peak and valleys they need to find. And they pick one of them valleys and peaks and they go, boom, there's our return signal. Or actually, that's two signals. We jammed them together. We didn't, though they were separate. We made a mistake. Oh, actually, that didn't happen. Now we didn't make a mistake. That's definitely a different signal within the time frame. And boom, distance confirmed. That's a radar bounce from Venus.
Right, because how strong would a radar signal be after traveling 150 million kilometers?
And back.
What's this? 30 million mile range.
Go back to the fig. Go back to the orbital fig. Two frames back, Shay. One more. And again. And again.
Which one?
To the orbital diagram you had.
To the one with Venus and the sun with the AU.
That was in the beginning.
Yeah, I went way back to get that. That's why I was confused.
Okay, well, just go back to it just for a sec, because you know where it is. There it is, lower right. Okay, there's Earth at 6 o'clock. There's Venus also at 6 o'clock. Does anybody notice that if this is what they're saying is the optimal moment to be bouncing things off Venus and back, that they're also firing them in the general direction of the sun?
Yeah, I did.
No possible conflict or interference there, boys. Just look the other way.
Well, I think they do it. because the sun is deemed to be a perfect black body, so it wouldn't be able to reflect. So it's like the one point in time where they have like a background that can like
Yeah,
not reflect.
but since whenever has the emission of the sun been constant anything? You know what I mean?
Oh yeah, like how do you know you're not just getting emissions of the sun and treating it as your signal?
Exactly,
Yeah,
exactly.
yeah, pretty
Not
wild.
too suspect at all.
Yep. Crazy. Crazy stuff. So, summing up one of my favorite NASA papers, which put forth about the constants being heavily reliant on each other, was also some other things they say was the rate of determination of the AU is actually heavily reliant on theoretical models, the measuring of these constants with residual uncertainty, and the signal processing complexity, which I think is also a very fair argument. So not only are they getting those signals back, but they're interpolating which ones are not noise, even though they essentially look identical. There's all sorts of other things you could, I think, critique that they have this dependence on planetary ephemeris, except when they started getting different measurements based on this new AU measurement based on the radar ranging they just completed and verified, instead of saying actually our radar ranging is wrong, our model of the solar system is wrong, this isn't where it appears to be. What they did was update the ephemeris with a different position and say, actually, no, we're super duper right, so that we'll just move where we think the planet is when we reference it for other measurements. And that's, going the other way with science. Anyway, velocity of light, of course, is a big problem. C plus V would throw, again, this whole thing into the works, and it would immediately break because we know it's actually not a constant. So this whole thing is based on, as we saw before, inherent mathematical ratios and nothing actual finite and limited to the world.
Checkpoint 3 there. Plasma effects. Now, which thing in the heliosexual solar system is the primary emitter of plasma?
Definitely not the giant sun that we're aiming at.
No, it's definitely not that. And that's the word that does not occur in point 3 at all.
Difficult to understand electromagnetic propagation effects, though. So
Yeah, this is so entertaining. Continue.
I mean, that's a valid concern. Like, hey, if you have all this plasma interference when you're aiming at the biggest generator of plasma in the known solar system using it as a giant backdrop, and do you think that would have an effect on these giant radar return bolts? Nah. Anyway, moving right along.
No, and I'd stake my PhD thesis on it.
Sure would.
And
Peer review that. Yeah.
they're going to stake their decimal points on it.
So this is another corroborating paper put forth where they measured the distance to Venus using the same process by the lads Malling and Gollum. Gollum, I think, Gollum or whatever, I think was an important dude who did some stuff later, I think, that we'll talk about before the end, I think. But he also put forth this paper, and he's known, a new value of 149,598,500 kilometers for the astronomical unit using this radar super sensitive equipment. So, I mean, if you want to replicate this, all you'd have to do is get a crane, get a ship, get a bunch of metal, build one of these next to your shed in the middle of the desert and in the middle of the night. And then you can have the super sensitive radar equipment and a high gain, low noise, 85-foot parabolic reflector so that you could pick up this super nice gain. Make sure you have whatever this is for this master amplifier so that you can actually be prepared to use the power that is this wattage, even though it's going to be transmitting at whatever all this is. You help me out here, Stone. You're asking about the parameters. Is this something that people can replicate, do you think?
Yeah, as long as they've also got a 2.4 gigahertz, transmitter. But it's at the top of table one I wanted to point out, just to get close to people's mindset about what kind of magnitude of power are we sending up into the sky. And there it is at 12.6 kilowatts.
That's a lot.
That's 12,600 watts. Okay.
How many hair dryers are we talking? I need this in a unit I can understand.
That's pulling 100 amp out of your wall socket.
It's about 8 hair dryers.
What?
Right.
What the ruck?
It's about 8. Your hair dryer is like 1,500 watts, right? It's about 8 of those. That's how much full power we're talking about.
8 hair dryers worth of signal into the sky.
We're supposed to be sending that 30 million miles over to Venus and then back. Oh, yeah. Again, loving figure 2 over there with a complete lack of magnitude for any of those amplitudes. I just love
Yeah.
it. So scientific.
Now that you mentioned the first one, I do notice that these secondary graphs are exactly the same, and when they specifically absent
On
the one that
purpose,
would make
dude.
it relevant. Yeah, that's funny.
On purpose. Can you
Look at our
like?
graphs though; it goes up and down.
Oh, dude. But by how much?
It doesn't matter. Don't worry about it. By the appropriate amount we were looking for, obviously. Anyway, all right. So look at the equipment from the top. This is what we're looking at. Again, you can replicate this. Just build one of these giant government facilities with an 85-foot parabolic transmitting receiver in your backyard, and you can replicate this super experiment. Which I guess you would need all these components actually too. What the mixture, the oscillator, you have an audio filter, make sure you have the square law detector and that low pass filter set up in the software to make sure you have the keying oscillator down to whatever that 64 CP is over here. And don't forget the last part to check with the ephemeris that we've updated to correct for the range and time for the time that we know that you've received the signal.
Ooh, you also missed your RF oscillator, which helps control the signal that you're sending out so you don't accidentally send out the wrong SIGI.
Oh yeah, that's way over here to the side on the other side of our circuit over here. Venus radar with non-synchronous open loop receiver. There you go. That's what we're looking at.
So I got a question on it. When we sent out these signals to Venus there to make sure that it was the size of Earth and all that good stuff, how did it know to come back to us?
Well, so we knew exactly how long it would take because we knew how long it was going because we know the distance to the AU based on parallax angles to Mercury. So when that required time elapsed, we looked really hard at the receiving data we were getting continuously since we started listening to it. And then we looked at it real carefully during that time and we picked out among the noise that looked identical to the signal we were looking for, the precise signal we were looking for, just when we were looking for it, precisely when we needed to find it.
So would it be fair to say that it's basically just a infinitely expanding wavefront that by the time it would get back to us would be so minuscule and nothing that it would like it would just be it would be literally background noise. Like isn't there a background floor for the noise or whatever? So it's like you have to figure out what that is, and then what you're gonna get back is gonna be can't be lower than that, otherwise it would just be noise. How would you pick out your specific noise from the random like it just doesn't.
Well, you have this giant dish. What you do is you get a 85-foot parabolic reflector, and then you can tell all noise. You can differentiate anything. Literally, you can find
tell all
any
noise.
needle in any haystack. Yeah, like whatever you're looking for, you found it. This is like the PCR test for the sky, bro. You can find anything, anywhere you're looking for it. Okay.
It's worse than that. Can you go back to that diagram? So where it has a narrowband IF amplifier, doesn't that mean it's just amplifying the specific frequency they're looking for?
Yep. That's definitely part in the paper. They said they did this a lot, and that actually it's part of the process, which they knew they were going to get it, and they did it specifically in the gap so that when they were looking for their required signal, it would be super strong.
Yeah.
Obviously.
So similarly to how they say, I forget, I think it's like Voyager 1 or 2, the one that's like 20 billion miles away from us, the signal that it sends back is like less than anything, but the way that they like articulate it is that they consider the satellite array system that they have, the deep space network, with all these like amplifiers in it, that they're essentially, that their argument is that they have a big catcher's mitt. So they have a really small, ball that's going out, being sent back, but they have a really big catcher's mitt. So they're just amplifying that to infinity, very similar to the LIGO stuff, dude. It's actually, this is like I
noticed a lot of parallels. Yeah.
Yeah, this is like how they did it the first time. They're like, can we just redo this thing we did with the sun? And they're like, well, nobody seemed to notice and we got funding. So yes.
We definitely got away with it last time. So yeah, why would we not do that? Not do it again? So they said they upped the power by 30% when they didn't get it the first time. Then they doubled the frequency, whatever, to overall the receiver sensitivity up by whatever 180 dBms. And it's one of the most sensitive at any time and for any purpose anywhere in the world. So you definitely know that if there was something to hear, dude, they heard it. And it was a clear cut. And they said, look, the very first time the system was tried on 10th March 1961, as we said before, there was a clear success had been achieved. 60-second constant in the post-detection filter. When we brought into the beam of the receivers, we knew it. They knew it. So they got it exactly what they were looking for when they were looking to find it. Again, just some more objections to what we just went over scientifically based on limitations, amplifier signal interpretation, signal against cosmic noise, not accounting for plasma, variation on the speed of light, all the main tenets that we've been putting forth the entire time. Here's another paper by a lad. I don't think I can pronounce his name, Semikov, from I think for obviously Russia. And his main argument, reading all of the preceding papers, was that the speed of light, as used in the calculations and prescribed by the special theory of relativity, has to be constant, which is then added to the signal. But he also noticed that actually it's not constant, and that would be a problem for most of the calculated AU, the period equal to days, the relative speed of the Earth, deviations of calculated distances of Venus, values measured by radar, and everything that we know in astronomy. And this is his main point, is that using the parallax angle and measurements and the distances that we just went over and calculated and figured out, actually that would be a big problem because of you guys' relativity and the speed of light, and that you have all these unexplained anomalies. Let's see, so like literally what you're saying, his whole premise is that it's not constant. We know it's C plus V, and that introduces a whole set of errors and deviations in calculations, including the value of the AU, which again is what we are putting forward. And I just thought that this guy got published objecting to all the same things that we were objecting to. So, to summarize, again, calling on the flat earther formerly known as Jaren to give us that most of the solar system is just math, covariantly scaled in an internally consistent system with ratios defined by Kepler and different periodic relationships based on observed periodicity. It sounds like a lot, but it's really simply explained by Jaren when he went over, look, if the only thing you ever observe is something is 0.53 degrees, then 31 or 32 arc minutes, then you could easily tell everyone that it's this far away and this wide, or this far away and this wide, or this far away and this wide, etc., because the only thing you observe is this. And through a system of covariant scaling and carefully applied ratios through Kepler's observations, and now we've also learned selectively applied ratios through internal physics constants, then you get an internally consistent system, only ever specific with ratios. And that's pretty much it. That's the distance to the sun. That's how we knew it.
Whee!
This guy's super exuberant because he found his detection from his telescope that he sent over here. He got it back instantly. He found the sun.
Great,
awesome.
Prezi. I got a quick question. The meme you put up with the sun distances, I can't remember if you said, but what's like the main factor they kept changing or having to change, or was it for a bunch of different reasons? Or
No, they just would literally manipulate the diameter of the sun and the distance using this thing. So they would get these two variants. So then if you're only keeping this a constant, then these can vary. Then all of these people can just vary these two to get a different, like what they don't tell you is that each one of these distance predictions had a differing diameter of the sun to go with it to satisfy this angular resolution, angular diameter formula, which they were just using. This was the formula at the heart of all these guesses. That they know that it's 0.53 degrees, and they can just change little d, which is the diameter of the sun, and then big D, which is the distance. So like they just change these two independently. That's how they get
who's
it.
got the bigger D contest. But yeah, so it sounds like they're just trying to. I mean, there was no actual reason they needed to change the distance, or just like what happened. I guess I don't. Yeah.
I'm not even like I couldn't verify that all these people actually made these predictions. What I can verify is that someone laid a very nifty breadcrumb trail that would look like the historical record of all these predictions to evolve into this one astronomically correct prediction.
Gotcha.
Because they specifically leave out that all these had an equivalent diameter prediction that they just don't. If they gave that, it would give the game away. So they just say, look at these different distance predictions. Don't tell you how they did it. Don't tell you that they're all related by a ratio anyway in the first place. But that's definitely like the main the main reason, the main thing people will cite when they go, that's how we know distance to the sun. And then the other people will loosely point to stuff like this, where you have interpolated noise that's definitely not a solar echo, that is actually a radar return from the thing you're looking for right where you're looking for it. mctune.net / whatever that is, echoes radar echoes from the sun. Go read that paper, waste your time. It's only like 6 pages. Yeah, there we go. Any other
Awesome.
comments, questions?
None. That was great, man. It's a great breakdown. I think the most
Nice.
pivotal piece there was the citation that was given that, basically reiterated our argument, is that all of these numbers are ratioed against one another to make an internally consistent system, and that they're not being independently verified in any meaningful way. Yeah, right there. This idea has not been realized even today. Super unlucky. And that's
Yeah, this would be
That's
like
2003.
Yep. This would be what I would loosely like hypothesize if I was on the outside, do nothing, and I was like, well, I know that they're not right, but how are all this stuff working out? You know what? The constants that they say are independent must not be truly independent. They must be interrelated in some, not visible way. And lo and behold, this dude at NASA putting out a JPL paper saying, hey, has anyone independently confirmed any of our constants? Crickets. And buried.
Yeah, that's a
Yeah.
great way to yeah. So earlier we were talking about, like, in terms of debate, how would you deploy this information if you were confronted with someone showing you the distance over time equation and plugging in the speed of light and the
Right.
distance to what is it, the astronomical unit or whatever, and it comes out to be what it is? Well, you would have to go into the how this was all computationally processed, the post-processing aspect of it. You'd have to get into what the actual measurement was. What was the amplitude of that noise versus the other background noise? So this is great work, man.
I like how you showed that guy's math too, that professor, and how it kind of all comes back to the radius, you know.
Yeah, so I tell Globers that, and they ignore everything I say. So I was looking for a different approach where maybe some neutral people would actually absorb it. So I was like, all right, what if we take it to like physics 101 to the professor looking dude who you might just listen to without animosity? Figure they tell you the same thing. And yeah, like he just slid it in there, and I think he did a good way of demonstrating it. If we just show that actually what you supplied was the key to everything. And here's why. Because now you give it a metric equivalent. Now it has a value, but it's only ever been part of the ratio that you used in the first place.
Like, hear me out. We'll use central angle theorem to derive the radius of what we're standing on. And then we'll use that same radius to derive a bigger
Everything.
bigger
Everything
central
else.
angle in a smaller central angle in a bigger system.
And we'll just keep doing that with every orbiting body until we know, based on Kepler, what the ratio, like if it's 0.7 AU, and we know that AU equals how many units of radius or whatever, which is what it comes out to, and it's all they're measuring. It's kind of crazy. It's all built upon itself.
Well played.
And it's like, oh yeah, but how did you actually empirically measure? Oh, well, we use the only thing that flat earthers have ever managed to falsify, the radius. Like, oh, solid. We'll take it from here.
So
Then.
so real quick, did they use 7/6R radius, or did they use the 3959 exact? Did they use two different polar estimations based on the undulation of a geoid or was it just the regular radius that everything is actually based off of?
Yeah, 6,200 kilometers.
Yeah,
3959.
so exactly 3959. Okay, just double checking to make sure.
Yep, good stuff. So yeah, when I first looked into it, I was like, D equals VT. I'm like, wait, how do I wait? Hold on. What he said was
It's like, how do I fight
convincing.
this one? Oh shit!
Yeah.
It's like you can't. You have to go at it from another means.
Yep, focusing on the wrong side of it. Okay, I get you. They're really good at what they do.
This is a great prezi, Shane. It was very, very interesting, and kept you interested in paying attention. I just also wanted to say that I find it very odd that we can see the constellations, right? We can see the stars, right? But yet over thousands of years they just don't move. Like, what's up with that? If they're large enough to be seen, we should be able to see some motion of everything moving.
Well, what if they were infinity away? How would you know how much they move by?
Yeah, it's very convenient. So they just said, oh, it's trillions and trillions of miles away. And so you can't detect any motion whatsoever.
Yep. Yeah, but trust us, bro. We know the distance of everything in the universe.
All
Because
right,
if you
well,
can see a star in the sky, it's occupying a certain amount of space, right? Yeah.
yeah, but Lily, what if the space in between the stars was infinitely expanding 3 times the speed of light, and it just always looked like it wasn't moving because because what's in between them is actually what's moving? Then what say you?
Wait, my brain just got pretzeled.
That's what they did to everyone. They pretzeled everyone's brain and was like, oh, well, it's actually stationary there because what's in between is expanding. Pretty awesome, huh?
Yeah, I
That's
feel
great
enlightened.
Prezi, you guys. Great Prezi. Loved it.
Thanks, everyone.
Yeah, with that, I think we'll go ahead and wrap up for the night, unless you have anything else, Shane. Unless you're hiding another
Nope.
Earth radius in there somewhere or something, tucking it in.
Guys, I do like how important that Earth radii became at the end of it. It's so integral in the backbone of everything. And it's the only thing that flat earthers have done a great job of falsifying the shit out of. So it's a strong position for us to take.
Yeah. All right. Well, with that, we will wrap up for the night. Thank you, Shane G. Thank you, Kat, for the awesome announcement at the beginning, and welcome back. And
That wasn't the same with that.
yes, it wasn't the same without you. And Friday we'll be back for the community Twitter night with hosted by Brian Sweet and Ken. So we'll see what those lads are up to on Friday. And then Sunday we'll be back again where Shane will be presenting this again, and we'll go over that on Sunday for Globebusters. And then Monday will be celestial theodoliting, of course. So hopefully we'll have some new stuff cooked up by Monday for that.
I think we
All
should
right.
make one of the Globers uncomfortable and bring them to the forefront again. I think we had good results with that.
Yeah, we'll see what happens. All right.